Hi. Hi. Sorry, one sec.
Okay.
Okay. Hey, everyone. So, yeah, I have my preschool is closed today, so I'm watching Zella. So I'm letting Soham run our sesh today. If he runs into anything that he needs help with, just send me a Slack or a text message, Soham, and I can.
Okay.
But yeah, I gotta go watch my kid since preschool's closed. Thank you, everybody. Nice to see you briefly. All right, take it away. So we just raise hands, by the way, and see what comes. So go for it.
Okay, perfect. I'll go for it. Okay. Hi, everyone. My name is Soham. I'm one of the TAs. Hopefully you've seen my name before. Okay. I wish there's like a way I can order which people raise their hands first, but we'll go with Ryan.
Wait, I definitely wasn't first.
Oh,
And it
okay.
was like Sophie or David.
Okay, Sophie, go for it.
Yeah, so my question was about disjoint sets and about the connect operation. So for like pretty much everything but weighted quick unions and like weighted quick union with like path compression, like we're connecting P to Q, whatever that means, whether that's like in quick union, like changing the root of P to the root of Q, or like in quick find changing like the set number of P to the set number of Q. Like, is that kind of how it is? And then in weighted quick union, it's based on the size.
Yeah, I mean, so any connect operation, we're basically taking two connected components and we're somehow like combining them together. In a weighted quick union, yeah.
I just wasn't sure like which one like what we're connecting to what. Or the connect operation. So I wasn't sure if like P, like, because I think it's like connect PQ, and I wasn't sure like which one we change based on the other.
Yeah. So if P is part of some like tree, Q is also like part of some tree, right? So in a weighted quick union, what we do is we take the roots of each tree, and we put the smaller root under the bigger root, right? Yeah, that's basically it.
Got it. But then in other cases, it's just like we just connect P to Q, like in some way.
Oh, so like if we have a quick union that's not weighted, how do we like resolve it?
Yeah, or like if it's a quick union or quick find, like how do we resolve what gets connected to what? Like what changes based on the other?
Okay, I see what you mean. So
yeah,
on an exam setting, we'll specify like for a quick union, it's sometimes arbitrary. Like, do we choose P under Q or Q under P? It's pretty arbitrary. So in an exam setting, we'll specify that.
Okay, great. And is that the same with like what would like create like path compression? Because I know that in some cases, I think is connected, like can create path compression, and same with like find. Or is it always find?
So yeah, so find will cause path compression if path compression is implemented.
Yeah.
Then is connected. Do you recall like how is connected works? Like what's the code for is connected?
I can't remember the code, but we would go down and we would check like if it's connected. So technically, like you could do path compression with it, right? Or
Ooh, okay, let's pose this question to the audience. Does anyone recall what's the code for is connected?
I'm pretty sure it just checks like the parents of both.
Yeah, and then how do we find the parents?
Like going through the array until like there's a negative, like you take like the actual value.
Yeah, we use find, right? So like if find implements path compression, it means is connected like inadvertently also like uses path compression because it calls find.
got it. Okay, so okay, I think I remember implementing that in one of the labs or something like that. So if we see is connected on the exam, we can assume that it uses find, which means that it would use path compression if that's what we're doing.
Yes, and we'll be like very clear if it uses path compression or not.
Okay, great.
Yeah.
Thank you.
Okay. I think David, I'm definitely.
Yeah, so I had quick doubts about project 2B. So first one was that my add operation for the array min PQ, the heap that I created, takes more time than the naive implementation. And I am thinking that's because the heap has to swim and sink every time I add something, whereas the naive implementation doesn't do that. It just adds it to the array. and so it makes sense. But I was wondering if that shouldn't be the case.
No, I think that makes sense. That's reasonable.
Okay, and another thing was that my size and get smallest methods are definitely constant time the way I've implemented them. But when I, for example, run over a loop of 1,000, like a 1,000 loop, and call get smallest twice, like one loop says for int I equals 0, I less than 1,000, and I keep calling get smallest. And then there's another loop that I create and I call get smallest. But both times there's like slight difference in the time it takes. Is that fine, or should it always be the exact same?
I think that should be fine. There's like, I mean, the get smallest code is in essence constant time. So I wouldn't like think too much about like minor changes in the times.
Okay, that's it.
Yeah. Okay. Let's see what other questions we got. Okay. Yeah, once you guys like answer a question, I'll lower you guys' hand. Okay. Ryan?
I have a couple questions on midterm 2016 spring.
Okay, let me pull it up.
All right, fine.
Yeah, okay. It might take me like a second to like look at the question. So
You good.
okay, which midterm again?
Spring 2016.
Spring 2016.
Hug.
Yeah. Okay. Perfect. And which question?
I have a couple. So the first one, can you go to 5B? Like this is just a quick one. So like for the worst case, like it's like n squared. So like I'm just like, so let's just assume that like the hash code like sucks and it's just like return. Is that like what it's saying? Because I thought like that, like we assume that the hash code is fine. So then like,
Yeah.
but in this case is like the worst case, so it puts everything in one bucket, right? So I'm just assuming like that's what they mean, like the hash code.
Yeah, exactly. So the hash code may not like suck, but there is like a possibility that even with like a good hash code, they all go to the same bucket just because
it's a multiple or some shit.
Yeah, it's like a multiple. You know, it's like there is like that small like really edge case possibility, and that's like what we're considering.
Wait, could you like not like flesh that out like really quick? Because like me and Hug went over it last time, but like I didn't really get it.
Okay, so let's say like we have an array. Let me share my screen on my iPad. That would be cool. Give me a second. Okay, perfect. Okay, so I think you guys can see my screen. Let me just move you guys to another window so I can see you guys as well. Okay, perfect. So let's say that we have like some hash map. Okay, and let's say it's like 0, 1, 2, 3. So it's size 4, right? So let's say like we're inserting some numbers in here. Like if I insert the number 3, it would go right here, right?
Right.
Like if we insert, I don't know, 7, it's also going here, right? So like there is a possibility that if I insert like n numbers and then they're all ending up in the same bucket.
Is that just by chance, or is I know there's like something to do with like multiples, right? Like what if it's like a multiple of like one of the numbers or something?
Yeah, so like we could think about it could be multiples, but for this class, if you just think about like there is a chance of this occurring.
Yeah.
So the worst case possibility accounts for this chance.
Okay.
Right.
Sounds good. But then when we talk about like hash maps, we always say O1 amortized.
Yes.
And that's under the assumption that there's a good hash code, or that it's like, or like not good, but like it's like randomized.
Yeah. So usually like if we have a good hash code, then we can assume like a good distribution. But
okay,
there still is like that worst edge case situation of all of the, I don't know, items going to the same bucket.
Okay, and then can we go to 9 real quick? I have like 2 questions on number 9.
Yeah, let's go for it. Okay. Oh, asymptotics, I love it.
Yeah. Okay. So for like the last one and the the third one, like the explanation like added up like all like the different like frames, or like for example, let's go to the third one. Like the explanation added like 1, 2, like all the way until like 2 log n.
Mhm.
and like that makes sense. But I thought like that's like the number of like calls like the entire function, right?
Yeah, sure. I can quickly like draw like a quick diagram for this question. Let me just take a sec.
Sounds good.
Okay. So how I like to approach like asymptotic questions regarding recursion is I like to draw a diagram. So how this diagram works is for each recursive call, we're going to draw a node. Okay. In this node, we're going to have two attributes of the node. Okay. We'll have the input size. In this case, the first call input size n, and we'll put the work that we're doing inside. So input, okay, and then work. Okay. So what we want to do is we want to draw like a tree-like structure to represent these recursive calls, right?
Right.
So like quickly just drawing this out, we see that's like n, then n over 2 at this level, right? And we can kind of see that we have one more. I usually like to draw 3 levels because then I see the pattern in the tree, okay? So after drawing like 3 levels of this tree, we want to figure out the work per level, okay? If looking at the top level, we see there's 1 work at the top level, there's 2 work at the second level, there's 4 work at this level, and so on, okay? So you can kind of see the sum of the total work is 1 plus 2 plus 4 plus like, well, we need to figure out the height of the tree because the height of the tree is like the last term in the sum in a way, right? It kind of impacts it. So let's look here. This is like a bit of a jump, but I think it'll make sense.
Yeah,
If you
no, it
think
does.
about-
Yeah,
Does it make sense?
yeah, it does.
Okay, perfect. So
And then like the height of the tree is log n, and then like you do like 2 to that power. Like that's
Yeah.
that number, like the last number is like the number of nodes in the bottom row, right?
Yeah.
Is that correct? Okay.
Yes.
sounds good. And then could you quickly go over the last one on this page, and then I'm done.
Yeah. Okay, let's quickly. Okay, let's go for it. So n squared. Okay. Okay, this makes sense. So what's happening here is, okay, how I like to like draw these like nested loop problems is, this is like not as official as a tree recursion way, I apologize. But I just like to think about, I'm entering this like for loop several times, right? I think it might be helpful if I'm gonna quickly pull up this problem on my iPad just so other people like have a reference.
Fact.
Okay. Give me.
I was just confused, like if there was like any like thing to do with log, because like the outer loop goes by log.
Ooh, okay. I see what you mean. Let's give me 1 second.
Yeah.
Okay, perfect. We can share again. Okay. Okay, where is this question?
Scroll. It's like number 9.
Okay, perfect. Nice. This one, right? Okay, so like the first thing I like to do when I look at this question is we have this outer for loop, and each time it enters, like each time we enter an iteration of the for loop, we do like some amount of work, right? Or this for loop goes for like some number of steps. Okay? So like let's just count out how many number of steps it does for each like value of I. Okay? So the first time we enter this for loop, I will be equal to 1, and we'll do like 1 step, right? The second time we enter, I will be equal to 2, and we'll do 2 steps. The next time, I will be equal to 4, and we will be doing 4 steps, and so on. And we can see that eventually I will be equal to n squared, upon which it won't exactly be equal to n squared, but like asymptotically, it's the same thing. So we see we get this sum. And if you guys
Wait, it will be equal to n squared.
Does it actually become equal?
Oh
to
wait, no, not necessarily.
Yeah. Like we don't. It doesn't matter though. We just know it's
Yeah.
like within some constant factor of n squared. That's
Right.
what matters.
Uh-huh.
And then we get this sum right here, and then we see that like this is a dominating sum. I like to think about a dominating sum as like the last term matters, the other ones don't. So we just look at the last term of the sum.
For real? Like, you just get rid of all the rest of them? I mean, they're so much bigger than the other ones. That's the
Yeah.
thought process behind it.
So mathematically, if you think about 1 plus 2 plus 4 plus like any other number, let's just look at a small example. 1 plus 2 plus 4 plus 8. These numbers prior to the last term will always be the last term minus 1. It's pretty cool.
Oh, wait, yeah, facts.
Right? That's kind of cool. So like,
Yeah.
if it's equal to last term, like, I don't know, we can just ignore them. And then we know the last term is like the one that actually matters.
Uh-huh. Like, okay, so like I should think about like these problems as in like it's the runtime is dependent on n squared, kind of. Does that make sense?
Ooh, okay. The runtime is dependent on n squared. So yeah, you could maybe think about it like that. I'm not entirely sure what do you mean like dependent. Like, what do you mean
Like
like dependent on n squared?
like it's well, yeah, it's just determined by n squared, even though
Yeah.
like in this case would it be more like 2 times n squared, but then you drop like the 2?
Yeah, so like just ignore like constants, you know? Like
Okay.
ignore coefficients, ignore constants. It's just n squared.
And I just need like a little help like making the jump, like so we don't do anything with log in this problem?
So the reason like, yeah, there's no like, I don't know, official log in the solution, and there's like no log used in the question. I think when a student, like anybody looks at this question, it's easy to see that this looks something like log, right?
Facts. Yeah.
But what's like the best way of approaching it is think about we're doing like a certain amount of work each iteration of the for loop, right?
Right.
So if you like lock in into this log n mentality, it doesn't work because each iteration of the for loop doesn't do the same amount of work, right?
Right.
So you can't do like log n times 5 or something because we don't do 5 work every time we enter the for loop. So like
Mhm.
we can't really use that log n mentality if the for loop is doing a variable number of work each iteration. Is that gonna make sense?
Yeah. Okay.
So
Yeah.
just to follow up on that, like
Yeah.
the reason why we kind of like it seems like we're kind of ignoring the inner for loop in a way. Is that because it's kind of dependent on how I scales?
Ooh, okay. So we're not like ignoring the inner for loop. The inner for loop is where we get these numbers like 1 and 2 and 4 from.
So we get that because it runs based on the outer for loop setting I.
Yeah, so like when I is equal to 4, we get mu printed out 4 times, and then 4 becomes in the sum because of that.
Got it. So let's say we had like the inner for loop was like j is less than n. How
J
would
is less
that?
than n. Okay, so in that case, what we're seeing here is we do the same amount of work each time in the for loop, right? Like we're
Yeah.
doing n work regardless. And then we can go back to Ryan's idea of saying like we have n work in the for loop, and how many iterations do we have like total? Well, we have like log of n squared, right? So if we have log of n squared iterations and we do n work for each iteration, we can kind of see the answer would be n times log of n squared.
Good. Okay, last question. If like so if you didn't drop the constants and stuff, it would be 2 times n squared minus 1.
So we don't like exactly know that I is going to be equal to n squared at the end, right?
But approximately, let's say
Yeah,
it is.
I mean,
Let's say
well,
it is.
yeah, I guess, yeah, you could say that. That's fair.
Okay. All right, fire. Thank you so much.
Yeah, you're welcome. Okay. Any other questions like related to this asymptotics problem before we move on?
Yeah, hi. So sorry, go ahead.
Okay, cool. Thanks. So I just got a quick question on this. So are we evaluating this like using the chart method, or are we evaluating this using the tree style method? So like where I draw the chart for my n input, and then I'm gonna go like 1, 2, 4, so on and so forth until I hit n squared? Or like how would we draw out the chart for this one?
So yeah, we would use the chart like diagram. Truthfully, I just like count each time how many times this for loop goes. So I'm like not too familiar with the chart method for for loops. I just say this for loop like each iteration of I, this orange for loop is going to get executed a certain number of times. And then I get the sum because of that.
Okay.
So yeah, I think chart method's like a bit longer, and I'm honestly like a bit rusty with the chart method. So this is
Okay,
like
cool.
the way I like to go about it. Yeah.
All right, cool. Thank you.
Yeah, you're welcome. Okay. I think we had one more person who spoke up.
Oh yeah, right. Right. So
Yeah.
just a real quick question regarding this question. So like essentially what we need to do is like, so we can essentially just like ignore like all like the first like all the first few cases except for the last case, where like in the end we will have like a for loop that needs to run like about like n squared times, which is essentially saying that we will have like a n squared runtime because
Yeah, so like you could think about it as we ignore the first few iterations. I like to think about it more along the lines of like the last one takes the longest time. So, and it's so much more time than the other ones that we just only like care about the last one asymptotically. You know, like your logic is like completely correct too.
oh, okay, got it. All right, thank you.
Yeah, you're welcome. Okay.
Wait, if instead of like multiplying by 2 in each iteration of the outer for loop, we added 1, what would the complexity be?
Yeah, good question. So let's look at that. The question is, let's say that we change this to plus equals 1. You guys are really testing me. Nice job. Okay. So what's going to happen here is now our sum will be 1 plus 2 plus 3 plus 4. Oh, are we keeping this one as j is less than I?
Keep it as j is less than I.
Okay, good. So let's walk through this problem together. Does this seem fair for the sum that we're looking at? Does that seem fair?
Yeah.
Okay.
Yeah.
So looking at this sum, like we've seen this sum before, right? This is the sum of the first n numbers. So in this case, if you like recall how the sum works, is we do like n squared times n squared plus 1 over 2 is like the exact number, right?
Yeah.
So if we simplify this, it'll become n to the 4th.
Ooh.
Does that make sense?
Yeah, that makes sense.
Nice.
You're just you plug in the formula for the sum of the first n numbers.
Yeah. Yeah.
So usually take like the last term in this kind of sequence and square it.
Yeah, that would work as well. Okay.
If you thought like that, like why, like how do you know to square it? Like you take the last term and then square it. Like how do you like?
So it's because taking the last term and squaring it is like a shortcut to the solution I arrived at, right?
Yeah.
Like, yeah, basically Sophie's like, oh, if we look at this formula right here, asymptotically what it's equal to is taking the last term here and squaring it.
Yeah.
Right?
Yeah.
So just, I don't know, just a quicker way of getting to like my solution. Yeah.
Mhm.
Okay. Any other questions related to like this asymptotics problem? Okay, so we had some people raising their hands for a while. Okay, let's move on to, okay, Jatin. I'm definitely gonna butcher the name.
Hi. So I took some practice exams, and I had just some quick questions. I'll put down what practice exams I'm working on in the chat with like the solutions. And I was just confused on a couple of different pieces when we were going through. So for question 2B, and if you need to like read the directions or anything for that, that's good too.
Give me a sec.
Okie dokie.
Come on. Oh, nice.
Oh yeah, this is a typo. It's fixed on TPB's one, but HKN they have a typo here. It should be like Hancock, not Payne or something.
Oh, okay, that was my question because I was so confused when it said Payne for that first question.
Yeah,
because
no,
it straight
I've
up
had like
said
multiple people ask me this. Like,
oh man, I was gonna go through some pain. Thank you.
Okay, that would have been a nightmare otherwise to do that one. Okay, I have other questions too. Then, so 4D in question 5, do we need to know how to do those problems? Because I wasn't 100% sure what to do for those two.
Okay, so are we still referring to the same exam?
Yeah, same exam.
Nice.
4D and question 5. Like at 4D was like they give us this chart and then they're like, oh, you got to know like A N to the B1, M to the B2. And that
Wait.
confused me. And then question 5, like, do we need to know that or is that out of scope?
Okay, give me a sec so I can like have the problem up.
Got it.
Can you repeat? Okay, I just want to have the problem up so we can look at it. Okay. Can you, which question again? Was it like
4D and 5? Do we need to know how to do those two problems or is that not necessary?
4D? Oh, okay. Okay. So I think I'll like to ask Josh on this one because if he covered it in lecture, I think it's fair game. I don't recall exactly like what he covered in lecture. So I'll ping him and then like see for this one. But my intuition tells me that it's doesn't seem like too relevant to like this iteration of the class.
Okay, and then same for 5. Do we need to know how to do 5?
Okay, there's regex.
Yeah, I have no idea if that
No,
was.
you don't have to do regex.
Okay, sick. And then I had one more question just to ask, I think, for the first round of me asking questions. So 8D.
8D.
Yeah,
This
it was
exam,
on
right?
yeah, it was on X trees or like Zella trees, I believe is what they called them.
Oh, I see. Is it the same exam?
Yeah, same exam.
Oh, beautiful. Okay.
And my question here for 8D was I came up with a different method from the one that was given, but I wanted to understand what the staff's thought process was going through it because my idea was just 2 for loops to affirm both of the properties, but I wasn't 100% sure if that was the right idea or what they wanted.
Okay. Let me like remember what this question is asking. Give me like 30 seconds.
Okay, cool.
Okay.
Thank you.
A Zella tree has a main tree property. Okay. Okay. So do you want to like, can you repeat like what you wanted to learn about this problem?
So I wasn't sure what method the staff used to get to this answer because when I did it, I thought it was just made more sense to use 2 for loops and just have each one check like the 2 properties. So the first one check like the min heap property, make sure every node is like less than the other. And then the other one was like just to check the in order traversal by I think going left, then visiting, then going right in the for loop. And I just wanted to make sure if that was correct because I got like an n log n or like an n level like runtime, but I wasn't 100% sure if that was like the right way to approach it.
Wait, so I think your algorithm is basically like is it taking in a zealotry and then making sure that it's actually a zealotry?
Essentially, yeah.
Okay, I think the solution here, which I think it makes sense to me like initially, is that we're given some array and we need to create a zealotry, right?
Okay.
So it's along the lines of like, we need to create a zealotry given some array. Is that like the intention you're going for? Or yeah, I think, correct me if I'm wrong, but I was like, it seemed to me that yours is like reaffirming or like validating if something is a zealotry or not. But
Yeah.
so I think we need to create a zealotry. See, that's like a subtle difference.
Okay.
Yeah.
Okay. So then how would you approach this, or like how would the staff have approached this, like
Sure.
using the right method? Because I want to make sure my method was right as well, or like that I got the method right as well.
Okay, so to approach this question, like I've had like a minute, but I think my intuition is that if we have any tree, it must be a min heap, right? So for it to be a min heap, we know that the root must be the smallest, right?
Yeah.
So if we're given any array, what we know is that, like in this array right here, the first thing we want to do is we want to make sure that the root is the smallest element, right?
Hmm.
Then what we want to do is we want to make sure that if we have any min heap, a cool property of like a min heap is that if we look at like the subtree to the left and subtree to the right, they're also min heaps, right? You can kind of think about it like that, like a recursive definition. So if we choose 1 to be the root of like the overall tree, the next like, I don't know, reasoning for me is saying, okay, I've chosen 1 to be the root. Now both my left subtree and my right subtree should also be min heaps, right? And you can kind of see like it lends itself to a nice recursive definition that the staff in the solution kind of utilizes, where the first thing we do is we find the smallest element. We say smallest element, you are the root. So to figure out the subtrees that are on the left and the right, we can just use recursion. Yeah. And then if we use like a pre-order traversal on this like way that we created the tree, it will give us the list back. Yeah. Does that kind of make sense?
Okay, so what you're saying is the method the staff used was they used the previous question as an example, and they followed those steps piece by piece to essentially create it. So what would I do, like if I'm given this, because I've seen this problem type occur on other exams, what do I do if I'm given this problem type on the actual exam next Wednesday?
Sure. So the way I like to think about like a multiple choice question, not a multiple choice, but like a multiple part question, is that we're making this midterm so that the previous parts should be like helpful for like the final part, right? Like I don't think that's like too, yeah, I think that's like a fair assumption to make. So we want like the previous parts to help build the intuition for like the final code writing part, right? So how I like to do it is when you're solving the previous parts, like when you're trying to think of some example, whatever, try to figure out like what logical like line of reasoning are you using, you know? And then if you kind of like make it a bit more formal, saying like this is exactly what I'm doing in the previous parts in these examples, then for like the final one, you can just reuse like the same logic from the previous parts. So yeah, these multiple choice questions, or not multiple choice, multiple parts, it's a lot of reusing like intuition from these examples in the previous parts. Yeah.
Okay, so on these multi-part questions, if I get confused, refer back to the previous pieces.
Yeah, exactly. And like ask yourself like why did like, I don't know, the previous pieces sometimes will be like find one specific solution to this problem, and then the code writing will be like generalize a solution for everyone, right? That's like, I don't know, maybe along the lines. So if you look back at like the previous part, you'll say, I found this solution. How did I find it? Well, I followed these steps, X, Y, and Z. Let's translate X, Y, and Z into a general algorithm. That's like usually the way I like to approach them.
Okay,
Yeah.
cool. Thank you. I will ask some more questions in a bit, but I'd like to give some other people a chance too.
Yeah. Okay.
Thank you.
So Anthony and Sherry, one of you guys had their hand up first. I don't know.
I'll go first.
Okay,
what
perfect.
reference sheets look like for lec25?
The reference sheet?
Yes.
Okay, so we haven't finalized the reference sheet. It will most likely be like a similar reference sheet to midterm 1 in that we will give you like any like data structures, any like functions of those data structures, and so on. Yeah, but a reference sheet shouldn't be too, I don't know, helpful. It'll just be more useful if we give like, oh, like we're using some hash map here. I don't know, like we have some external chaining hash map. Here are the functions that like you can use in this hash map. So yeah, we haven't like, yeah, I can't give you guys too much information on the reference sheet because it has not been finalized yet. Yeah, but similar to midterm 1. Okay, Sherry, you want to go for it?
Yeah, I asked this on Ed actually, but I did not get a consistent answer. So I guess I was just wondering, like, why? Okay, so sorry, I found the question. So it was about like insertion into a red-black tree,
Sure.
and I guess I can actually link the Ed post so you can see like the table, but the
I sent
idea
the
is
Ed link
yeah.
online.
So the idea is that like insertion into red-black tree is best case theta log n, which does not necessarily make sense to me. I guess there's been a lot of discourse here, but
Okay,
Uh,
good question. So what's your intuition for why it should be constant time?
well, my intuition is like it's similar. It's this because like if you look here, the best case for a BST is theta of 1, which makes sense to me because if you find what you're looking for at the root, then like you can just terminate. It doesn't matter how big your tree is. Like if you're trying to insert 5 and you see that the root is 5, you don't have to do anything else anymore.
Okay. So you're wondering, so are you talking about insertion or finding?
Insertion, right?
Okay, so in insertion, I think the idea here is for insertion that we have to like iterate, like what we're inserting isn't already there. Do you see what I mean? Because otherwise it would be find if we're like trying to find some element in the tree.
I guess that partially makes sense, but then why would insertion for a BST best case be theta of 1?
Oh, good question. So I can draw a quick example. Let's say that we have like a really spindly tree, and then we decide to add the new smallest element. What's going to happen in constant time, we'll add it right here, right?
Oh, I see. But then for that won't happen for a red-black tree because it's always already balanced.
Yeah, exactly. Does that make sense?
Yeah, that makes sense.
Nice. Cool question. Okay. So any other questions? Sorry. Any other questions like based on, I don't know, like
On
red
that
black
note,
trees?
like, how do we know to assume that it's not already present in the root? Like, if we were like asked that.
For insert?
Yeah.
Okay, so I think we'd clarify that, like if we're actually, if it's on an exam, like we clarify how insert operation works. But the idea here is that the insert operation, if we're inserting a new node, like it'll take log n time in a red-black tree. And the reason that this chart most likely has that is it doesn't give me much information about like the runtime of insert if there's like, we're accounting for the edge case situation where the thing already exists at the root. You know, like,
yeah,
it's just more of like an edge case that doesn't speak to the overall runtime of the insert operation. So it's much more impactful if you say insert takes log n time instead of like accounting for the edge case and saying like, okay, you see what I mean?
Yeah, in general, like I feel like best case aren't as like informative as like worst case.
Yeah, exactly. I agree. Like this spindly tree that I showed you guys, like it's cool and all, but it's not as, I don't know, informative as a worst case. Yeah. Okay. Yeah, good addition. So, okay. Sophie, you want to go for it?
Yeah, sorry to go back to this problem. Can I share my screen real quick so I could just show it?
Yeah, of course.
Sorry, do you know, I think you have to make me a co-host.
Oh, that's awkward. Yeah. Dang it. Okay, this is awkward but I'm not the host of this meeting.
Oh,
I think,
okay, that's all good. So
yeah.
it's the same problem that we were looking at before on one of the midterms, and I asked if we were to change like I to N instead in the inner for loop. I don't know if you
Oh,
remember that.
yeah.
Yes.
I think I have.
I'm trying to figure out kind of like the summation and how that would like how we could derive from that it's I think you said it was n log n squared. And so I just want to
Oh,
figure kind of looking at the sum how you would know that because it's easy to look at like an arithmetic sum or like a you know geometric sum and know how to figure it out, but I was wondering how we could like figure it out when there's log involved.
sure. So if we see right here, like, let's say that this is n. Okay.
I don't think we can see your screen, by the way.
Oh, yes. I stopped sharing. That is totally my bad. Go back to when there was like a whiteboard and it wasn't this awkwardness every time. But it's okay. Okay. Nice. This looks good. Okay, so correct me if I'm wrong, but like this is the correct question and the correct change, right?
Yeah.
Okay, brilliant. So let's like quickly walk through how we can solve this. So we see here that every time we enter this for loop, we do the same amount of work, right? We always do n work.
Yeah.
Okay, so let's like write some stuff out. If we do n work each iteration, right, we just need to figure out the total number of iterations.
Mm-hmm.
Okay, so this is like a bit of where the math comes in. But if you look at this for loop, how many times does this for loop get executed?
N squared times.
Ah, subtle. Okay.
Sorry, I mean it's gonna be like 1 and then 2 and then 4 up until n squared.
Yeah, exactly. It'll be like, so it'll be like 1, right? I will be like 1, 2, 4, and then eventually I will like exceed n squared, right? And upon which we stop. So
Would we like get a sum that's kind of like n plus 2n plus 4n and then
n plus 2n plus 4n.
if there's n work each iteration and there's like
Except the n work each iteration is like independent of these numbers here, right? The value of I doesn't impact the amount of work that we're doing.
got it. Okay.
So like the easiest way to think about this is if we have this, like these are the values of I that are changing over time, right? So we need to figure out like the total number of total number of terms that are here. Like what's the total number of terms? Right? That's the total number of iterations that we're doing. So the total number of terms in the sum is like log of n squared. Okay. So if we have like log of n squared terms, that means we're doing log of n squared iterations. If we're doing log of n squared iterations and each iteration we're doing n work, we see that the total runtime is n times log of n squared.
And then how did you get that the number of terms was log n squared?
Okay, so I think that's like a couple ways of thinking about it. Like the easiest way is like if you ever see anything where it's like you have like kind of this increasing, like I is like doubling each time, then you can kind of just quickly conclude it's n squared, a log of n squared. There's like a bit of math, and honestly, like for the sake of this class, you could just recognize that we have like this pattern here, and you immediately just like that just means log n squared. There's like some math behind it, but honestly,
Okay.
like yeah, you don't need to know.
Log n squared, but because like when the n was an I before, like because it was keeping track of I changing, then it wasn't log. We couldn't assume that log was going to be a part of the runtime.
Yeah, so like in the previous time, the work each iteration was changing.
Yeah.
Because of that, like what that tells us is we need to figure out like the sum of the total amount of work, right? Because it's changing over time. Over here, like we get the sum of like n plus n plus n. Like we still have a sum, but every term in the sum is the same. So all we need to figure out is the number of terms in the sum, which is log of n squared.
Okay. Yeah, okay, that makes sense. So if it's like if we see that line and the like for loop, the inner for loop isn't really changing based on the outer for loop or something like that, then like we can probably conclude that it's log n squared, but otherwise we should probably, try to figure out how the like change in I would change the runtime.
Exactly. Yeah. So like if you see the inner for loop is independent of I, right? Then what we can do is simply figure out the total number of iterations and then multiply that by the work per iteration, right?
Yeah.
But okay,
Thank
that's
you.
good. Good follow-up. Okay. So sorry, I'm kind of bad at checking the chat. Okay, nice. Okay, any other questions? I think, oh yeah, open floor.
I got one.
Go for it.
Okay, this is from a different exam, but I still have the question, so I'm gonna put it in the chat as well.
Yeah, go for it.
And I'll give you and then so the
love
question
HKN.
So the question I have is from 2C, and it's kind of a hypothetical one. So I'm gonna wait for you to get there first
Yes,
before
yes.
I
Thank you.
ask it.
Okay, my speed in moving to the iPad is nice. Okay, I can just look at it here. 2C.
Yeah.
Oh,
So I figured out what was going on in the initial problem when I got it because I was confused about it. But now I have another question, which is you see the line where it says first list dot add last one, and it changes the list to be that value now. My question is, what happens if that were a 4? And because wouldn't then the indexing just be the same?
Okay, give me a sec. I want to like
Okay, cool.
understand what this problem is doing. So we have some list of 1, 2, 3. Is this X list just like, oh, I see. So a hash map is mapping a key value of an X list. Nice.
Yeah.
Okay, brilliant. So then we have this X list, and then we put cat. Okay, then we add last. Okay, and so you're saying it's like, what if we added 4 to the end?
Yeah, instead of 1, because you have to add up all the elements in the list to calculate the hash code and then modulo it.
Sure.
So it would go to the same area in the hash table or in the hash map because of that. So would that change how the function looked, or would it be exactly the same?
So in the case that like the hash code somehow changes and still gets mapped to the same bucket, our function would work properly just by luck.
Okay.
Does that make sense?
Okay, so the function would work as normal for 2C.
Yes. Yeah. Like,
okay, that makes good sense. Yeah. Okay,
Yeah.
cool. That was just like I was a little confused on that one when I was dissecting it because like there was one piece where it didn't go into the third bucket, it stayed in the second bucket, but it was asking to go to the third bucket. It just got a little confusing as I went forward with it.
Yeah.
So yeah. Okay, cool. Thank you.
Hi. Yeah, you're welcome. Okay. Do we usually like end it like right at 2? Like, how does it usually work?
Yeah. All right.
Okay.
I just sat down for our meeting. Yeah, I think we're done. Cool.
Okay.
I only caught the last 2 minutes of that. I hope that was fun, Son.
Yeah, it was a lot of fun. Thanks for
It is great. I enjoy it. Hi, everybody. All right. Well, I guess we'll go to our other meeting now.
Yeah, let's do it.
See
All
you
right.
guys
Bye,
Monday.
everyone. Good luck for the
Thank
midterm.
you.
You're welcome.